Okay, so we have a problem here where we have to do a couple of things. One of those is find the magnetic flux through that loop of wire. And we also eventually have to figure out, using Faraday's law, we have to figure out the induced EMF and the induced current through the wire. What makes this problem a little bit more difficult is that in order to induce a current, you need a change in magnetic flux. So the current is changing as time changes. The other piece that makes this a little bit difficult, though, is that the B field is not uniform as you go in the Y direction. So if we say this is the Y direction going up, the B field is going to change as you go upward. So to start here, we are given a current as a function of time. It's alpha times 1 minus beta t, where alpha and beta are positive constants, t is time. And the first thing we have to do is figure out what direction the magnetic field is inside the loop due to the current at time 0. And so to do part A, we can just use right-hand rule, where your thumb is going to point in the direction of current, and then your fingers wrap around that wire, and that shows you the direction of the B field that it's creating. And so if you point your thumb to the right, your fingers wrap around out of the page towards the top above the wire. And so for A, B field is out of the page. B is out of page. So part B, we want to do a couple of things. First part is to find the magnetic flux through the loop as a function of time, and then in terms of all of those values that they gave us earlier. So for part B, we are going to be using the magnetic flux equation, which says the magnetic flux equals the integral of B dot dA. Okay, if the B field was uniform, then we could just use B times A, for example, or B times A times cosine theta. But it's not uniform because, like we said earlier, the B field is going to change in the Y direction. And the B field caused by a current carrying wire, a long current carrying wire, looks like this. B is mu naught I over 2 pi r. Okay, I recommend that you memorize this equation, but if you didn't memorize that, you could always apply Ampere's law to get that. The couple of things here change. The current is going to change as time, so I'm actually going to leave it as I, and then at the very end of this, I'll plug in that equation for I, so I don't have to keep writing that out every time. But then we are going to replace this R with Y, because I'm saying up is the Y direction. And then to the right would be the X direction. So what we have to do in order to apply this integral is we need to split this up into tiny pieces of area where we can find the flux through each tiny piece of area and then sum that up throughout the whole wire, or the whole loop of wire, just like you would in calculus. If you were given a function and you wanted to find area under the curve, the way that you are applying calculus is you are splitting that up into a bunch of tiny rectangles where each one has a length of dx, each rectangle has a height equal to the function given, and you're finding that area, f of x dx, and then you are integrating that from your whatever limits you're supposed to, so x initial up to x final. So we're doing the same sort of thing here. We're going to split this up into little pieces of area, and I'm going to split it up so that every rectangle has a length that is equal to c and a height that is equal to dy. And the reason that I split it up into rectangles like that is because the B field is not changing in the x direction. So I'm just going to give them all the same length in the x direction, and then each one's going to have a different, each one is going to have a height of dy. So now I can rewrite dy as the area of that rectangle, which is length times width, or c, actually I'm sorry, it should be dA. dA is equal to c times dy. And I can plug both of these into my integral. Also, the dot product, you have b dot dA within that integral. The b field is out of the page. The area vector is perpendicular to the page, and so you can just write that as b times dA. The cosine of theta just becomes 1. And so if I put all of that in my integral here, we're going to have integral of b is equal to mu naught I over 2 pi y, and the area vector is going to be c dy. And then we need to pick our limits, and we're going to go from the initial value up to the final y value, and we are integrating this from this point right here. This is where our rectangle starts, or our loop starts, and then we're going to go up to where the loop ends. So this is y initial up to y final. And you can see that the initial value is at a distance a away from the wire, and the final value is a distance of b from the wire. And so this integral is going to have limits y initial equals a up to b. The next thing I'm going to do is pull out all of these constants. Mu naught. Current is technically not a constant, right? It's going to change as time changes, but it doesn't change as x or y changes. So I can actually take that out of the constant. Out of the integral. It's a constant in terms of these spatial dimensions. And so we have mu naught I c over 2 pi, and that's it. And then we have our integral a to b 1 over y dy. And we can do that integral. That integral is equal to the natural log of absolute value of y. So that's going to be mu naught I c over 2 pi. And we're going to get natural log of y. Evaluate that from a to b. The natural log of y is going to become natural log of a. So this doesn't equal this. Natural log of a, top limit first. So natural log of b minus natural log of a. And there is a log identity where you can make that equal to the natural log of a over b, b over a. And so then our magnetic flux is going to become, we're going to have mu naught. I'm going to go ahead and plug in what I is supposed to be because I think we're done here. So I is supposed to be alpha times 1 minus beta t. And then times that by c over 2 pi times the natural log of b over a. And that's it for flux. So that's how you find magnetic flux if the B field is not uniform. Okay, so part 2, we need to find the magnitude of the induced EMF in the loop. So using Faraday's law, E induced, in your formula sheet, it looks like this. We have negative derivative of flux with respect to time. And they do ask for the magnitude, so we're not going to worry about any negative values. So we'll just get our answer and then get rid of the negative if we have to. So let's go ahead and do this derivative then. So we're going to have negative d by dt of, and then we're going to plug in the value that we just found in part 1. So that's going to be mu naught alpha 1 minus beta t times c, all divided by 2 pi natural log b over a. Okay, we can take anything out that is not changing as time changes, and if we do that, then this is going to become negative mu naught alpha c over 2 pi natural log of b over a. And what we're left with is the derivative d by dt of 1 minus beta t. So taking those derivatives one at a time, derivative of 1 with respect to time is 0. Derivative of negative beta t with respect to time is negative beta. And so we're going to get the two negatives will cancel, and we're just going to end up with mu naught alpha c beta over 2 pi natural log of b over a. Okay, so now part C. It says to show on the diagrams below the directions of the induced current in the loop for each of the following cases. So case 1, beta t is less than 1. Okay, so this is a little bit tricky, but here we have this current. I is equal to alpha times 1 minus beta t. Okay, and they're saying that beta t is a value that is less than 1. Okay, so if we look at this, if we have this value here is less than 1, then 1 minus something less than 1 is still going to be positive. So the current is still going to be going to the right. But as time increases, 1 minus beta t is going to be decreasing towards 0 as it gets closer to 1. So current, this is the current in the long straight wire, is going to be greater than 0 but decreasing. And if that's the case, then that means that the magnetic field is still going to be out of the page, but it will be decreasing as time changes. And so then if we think about using Lenz's law to get the direction here, you want to think about what direction is the flux. So we said the B field is still out of the page, so flux is out of the page. Then think about how is it changing. So B field is out of the page, that means flux is out of the page, but it must be decreasing since current is decreasing. So if the flux is decreasing, then we want our induced B field, using Lenz's law, to oppose that change. So your thumb is going to point out of the page to stop that decrease. That would be the direction of the induced B field in the loop. And so B field is, in this loop, is out of the page. And in order to create that B field, we need a counterclockwise current. Counterclockwise current. Okay, so a little tricky there. Part 2, we have beta t is going to be greater than 0. I'm sorry, greater than 1. So if beta t is greater than 1, then that means you're going to have 1 minus something greater than 1. That's going to mean that the current is now less than 0, which means that it's going to the left, and as time increases, that value is, the magnitude of that value is going to be greater. So current is moving to the left now, and it's increasing. So again, let's apply Lenz's law. If the current is now to the left, that means that the magnetic flux is actually into the page. So magnetic flux is into the page, and it's increasing because current is increasing. So using Lenz's law, our thumb is going to oppose that increase, which means that our thumb is going to be pointing out of the page again for an induced, these are the induced B fields. The induced B field must be out of the page using Lenz's law. And in order to create that out of the page B field, we need again, a counterclockwise current. So both cases, counterclockwise current. Okay, so now we want to figure out what the direction of the net force, if any, on the loop due to the induced current at time 0. Okay, so if we look at the top picture here, at time equals 0, the current is going to be positive. So current is positive, and if the current is positive and time starts to increase, then we're going to have alpha times 1 minus something that's increasing, right? And so that means that the current must actually be positive or to the right, but it's decreasing. So B field is out of the page, which means that the flux is out of the page, but that flux should be decreasing, which means the induced current at first is going to be out of the page also. So we're going to see a counterclockwise current in this main picture that we have. So basically the same exact as the other two pictures. And so now we need to look at the force on each part of the wire. So if you look at the bottom portion of the wire, it's in a B field that is out of the page. So B field is out of the page everywhere. Remember, it's decreasing as you go in the positive Y direction. So on the bottom piece of the wire, using right-hand rule, your thumb goes to the right with current, B field is out of the page, so fingers point outward, and then the palm of your hand is pointing down. So the magnetic force on this part of the wire is going to be down. Okay? If you look at the sides, so the right side, the force, so your thumb would go up. For the current, fingers go out of the page, so the force on the right side of the wire would be to the right. Force on the left side of the wire, if you try that, is going to be to the left, but those are going to cancel each other. And then if you look at the top portion of the wire, you've got thumb pointing to the left with current, B field is out of the page, and so we have a magnetic force up here that is in the upward direction. But even though the current is constant throughout that loop of wire, the B field is decreasing as you go in the positive Y direction, which means if we look at the magnitude of this force, it's ILB. That means that the B field is stronger at the bottom, since the B field is increasing as you go close to the wire, which means the force on the bottom part of the wire is greater than the top. So I think the net force for part D, the direction is down. Net force is down.